Hi everyone, thanks for checking out this video. So, okay, this is going to be the end of this series. This is the point where we're actually going to start putting together everything we've done in this video series so far, and finally testing it out on a real neural network machine learning problem. So, yeah, at this point we're gonna work on solving this MNIST dataset, which is basically a dataset that has images of a bunch of handwritten numbers, and the goal for the machine learning problem is to make a neural network to be able to classify which number it is. So here's where to find the dataset. You guys need to download it for yourself because it won't be up on my GitHub, just because I don't know what the rules are about like putting up someone else's dataset on your GitHub. But yeah, you can find it here. And then, yeah, I think you need to make a Kaggle account to be able to download it, but that's pretty easy. It's like free to make an account. You just need like, to give it an email address or something. Yeah, and then you can download it here. And yeah, so here's the link. I'll also put the link in the description, and the link is also in this notebook I'm using here. But yeah, just go to this link and then click download. And then it should give you like a zipped compressed folder. And then when you unpack it, you get this folder called archive, which has a bunch of other folders in it. So the main one we're going to be using is this training set folder. And then it has another folder inside it also called training set. And then it has a bunch of folders where in each one of these folders, it has hand-drawn images of these numbers basically. So this is the ones folder. So yeah, this folder just has a bunch of images that they're pretty small images, actually 28 by 28 pixels, so actually very small. But that'll be good because we don't want anything too large just for our test example. But yeah, it has a bunch of these images of these numbers basically. So here's yeah, like the fives folder, just for example. And yeah, this is a good like practice data set because it's kind of one of the classic data sets in machine learning that people use when they're starting out just to practice with. Yeah, we'll be able to solve this basically with a pretty simple neural network. We won't need anything fancy. It'll just be 2 layers basically. And we'll be able to do everything that we're going to do in this video with all of this code that we've written, all of this package that we've been like building out. This will be enough to solve this real machine learning problem in this video. So yeah, just make sure you download this data set and then just put it in your like local folder that you're running your code on, so that we'll be able to read it in basically. And yeah, let's get started. So just like usual, make sure you run all of the code that we have so far just up at the top so that we can keep using it. And then next we're going to be using this images package. So if you don't have this already installed, just install it with the Julia package manager like this. But yeah, we're going to be using this images package, so just make sure you import that at the top. And then I again just wrote another link to the dataset. Okay, now just to get started, before we do any of the actual machine learning, let's just work on being able to read in some of these images. So we're going to say, I'm actually just going to copy and paste this part, being a little bit lazy. Yeah, just going to say like image path, and then yeah, we're going to say archive, training set, and then let's just read in like the first of these 0 images. So we'll say the folder is 0, and then image 1. So yeah, we'll make that our image path just to try to read in one of these images. And then we're going to say image equals load image path. And then I think if we run this in the notebook, it should actually display this image. Yeah, and we could try out like other ones too just to test it out. This was, I think, the next one. It looks the same, but it's actually a different image. Try out like image 5. Yeah, we tried a bunch of them, but yeah, I'll just stick with this. Whoops, sorry guys. Yeah, just image 1 for now. And yeah, we're gonna load in that image using the image path here, and then we're gonna turn it into a matrix. So it's gonna say image mat equals float 64 dot image, and then we can print out this image matrix. And so yeah, this is just representing it as the actual matrix of like pixel values basically. So we can print out the size of this too, like check the shape of it. Whoops. And yeah, it's 28 by 28 pixels. And so yeah, this is basically telling us like the relative scale of each of these pixels. Yeah, and all these numbers are going to be between 0 and 1. So yeah, can't go any higher than 1 because they're already like normalized. But yeah, these are like the normalized pixel values for the image basically. So yeah, we have it now in this 28 by 28 matrix representation. And then what we want to do next is flatten it. So next we're going to say image flattened equals reshape image mat colon, and then we can print out the size of this flattened array. And yeah, so this is 784. So that's 784 is just 28 by 28. So this is just what it looks like when we've flattened that matrix to get it into a one-dimensional array, basically. Yes, that's just going to be a little bit of the like basic image processing. So I'll just say up here, maybe a comment like basic image processing. That's how we're going to actually like go through and read in these images. Okay, so now what we need to do is we need to write some code to to go through this training set and basically go through all of these folders and read in the images and save them in this like flattened array format, and then also save like the label of what digit they are. Yeah, so we want to do that for all of our training set here. Okay, so the way we're going to do that is we're going to start. Maybe I'll leave a comment at the top actually. Reading in images. So we're gonna define our base path to be archive training set to just get us inside this folder here, so that we can then go through all of these subfolders with the digits and read in the images. And we're gonna call our actual like pixel data X, and whoops. And we're going to call our digit labels Y. And X is going to be a matrix, and then Y is just going to be a one-dimensional array for now. So yeah, I'll just say here like image pixel data. And basically the shape of X is going to be n by 784, where n is just the number of images we're reading in. So basically each new image is going to be a row in X, and then it'll have a column for each of these like flattened pixel data points basically. So yeah, each row will be one of the images, and then Y will be the digit label, and this is going to be of size n. And just one-dimensional array for now, basically. And this is just going to tell us for each one of the images what the digit actually is. So now, yeah, I'll write a bit of code to like iterate over these folders. So we're going to say first for digit in 0 to 9, and that folder path equals join path base path string digit. Yeah, that'll just allow us to like iterate over these like subfolders here. Okay, and then for file in read directory folder path. yeah, just iterating over these like subfolders. And then, yeah, just gonna be a little bit lazy here, copy and paste a bit of code just to save a little bit of time. Whoops, I think I screwed up the indentation here. And then, yeah, so this is basically just going to give us the path to the image, and then we're going to repeat some of this like code from up here, just like loading in the image from the image path, making it a matrix, flattening the matrix, and then pushing that new row onto our X, or sorry, I should be, yeah. At this point, it's not a matrix anymore, really. It's just a one-dimensional array. And then, yeah, pushing that array as a row onto our matrix that we're keeping track of. And then also pushing the digit here onto our array of the labels. Yeah, and then after that, there's one more thing to do. So, like, at this point, I'll just tell you guys that the shape of X at this point is going to be 784 by n. So we want to actually transpose that, and we want to make it into like a clean matrix too. So we're going to use this line here to just say like X equals, and then this like H cat thing is like how you make it into a 2D matrix basically. And then this apostrophe here means transpose it. So flip the dimensions around to get it to be, I'll just say like transposing to n by 784. Yeah, so that'll flip the dimensions around to get to be n by 784. And then at this point we can, after this is done, we'll just print out the size of X. And then also print out the size of Y to just make sure this worked properly. Okay, so let's run this and hopefully it'll work okay. Okay, it looks like it worked. So we have 42,000 images, and for each image we have the like normalized value of each of the 784 pixels. Remember, that's our 28 by 28 image. And then for our labels Y, we have the digit label for all 42,000 of these images. Okay, so now we're ready to like proceed onward. So the next thing we're going to do is shuffle up these images, because right now that they all got read in order. So it's right now these are all in order of like 0, 1, 2, 3, so on and so on. So we want to shuffle them up for our like machine learning problem. We don't want them to be in any like predictable order. So what we're going to say here is n equals size of x1, and that'll just give us like n equals 42,000. And then this is how we shuffle both of them so that they'll be shuffled, but every label will still correspond to the correct row in X. So we're going to shuffle them randomly, but shuffle them in the same, so that they're still in the same order, even though it'll now be a random order. So we're going to say perm for permutation equals shuffle 1 to n. X equals x perm comma colon, y equals y perm, and I'm just going to give it a semicolon here just so it doesn't print out the output here. But yeah, you guys don't actually need that semicolon. That's just for the notebook, so it won't print anything out. Okay. Whoops, I think I forgot something here. I think this probably needs the random package. Yeah, so you need the random package to be able to do this shuffling. Okay, so now what we want to do is split up our data into a training data set and a testing data set. And we're doing this all with this training set because if you guys look in this archive folder, it includes a folder called test set. But I think there's some problem with this test set folder because it actually doesn't tell us the labels of these numbers. So I think maybe whoever made this data set like might have forgot the actual like digit labels because they're not in these folders like according to what digit they are. So yeah, we're not going to use that actual test set. We're actually just going to split up this training set into like a training set and a testing set, basically. Okay, so we're going to say train size equals integer 0.8 times size x1. So this is basically saying we're going to be using 80% of our images for training and 20% for testing. And then we're going to say x train equals x from 1 to train size colon y train equals y from 1 to train size. Okay, and then for our testing, we're going to say x test equals x from train size plus 1 to end, and then y test equals y from train size plus 1 to end. And then we can print out the size of each of these. Okay. So that'll be our training and then testing. Whoops. Okay, so yeah, we have 33,600 sample images for training, and then 8,400 images for testing. And just to remind you guys, the reason we divide into training and testing sets is because we're going to use our training set to actually tune the parameters of our model. But then to actually evaluate how good of a job our model is doing in the end, we want to test it out on images it hasn't already seen in the training. So that's what the testing set is for. We're basically going to withhold these testing images so that they're not used in the actual training of the model, so that when it comes time to actually see if our model is working or not, we'll be testing it out on images that it hasn't already seen, basically. So yeah, that's why we divide up into training and testing data sets. Okay, so now it's time to start actually defining our model. So I'm going to start by saying layer 1, and I'm going to copy and paste in a little bit of code here. So this is going to be the weights tensor for our first layer. So we're going to initialize it as just like a random matrix of numbers of size 784 by 128, and this means it's taking in 784 input features and has 128 neurons in the layer. So remember, our 784 input features is the basically the measurement we have for each pixel for an image. And yes, it's going to be taking in 784 input features and then doing the calculations for those inputs for 128 neurons. And the actual size of the input matrix is going to be size of input matrix equals batch size by 784. So we're going to be using a batch of samples. So if we have like 10 samples in the batch, then this input matrix will be 10 rows and 784 columns. So each row in the matrix will be a different image within that batch, basically, just like we did in our small example in the previous video. So yeah, it's going to be taking in just any number of images in the batch, but the important part is that each image will have 784 features, like input features. So then the output of this, well, actually, I'll talk about the output in a second. One more thing we need to define. And then for this layer 1, each neuron, remember, also has a bias that's going to be added. So each neuron is going to involve like some weight multiplied by some input feature for like all of the input features, and then a bias added at the end. So we're going to initialize this as just a like row vector of zeros basically, but these will eventually be tuned so that they'll have the option to like not be 0 anymore once we tune them. But we're just going to initialize them as zeros, and then yeah, this weights tensor, it's going to be initialized as random numbers, and we're going to scale them down so that they're going to be like small random numbers close to 0 basically. And then yeah, just a little test, we can just say like, okay, we'll say like batch x equals x train from the first row to like the 10th row. Say we have like 10 batches in our sample. Colon. You know what? Maybe I'll put this, just for clarity, I'll put this like up here. And then our first layer output is basically going to be like this. So we're going to say like layer 1 out equals batch x times weights, or sorry, forgot something here actually. This is important. This should be we should be casting this into a tensor, because right now this x train is just a 2D array. We want to make sure to cast this into one of our tensor objects. But yeah, then we're going to say batch x times weights 1 plus biases 1, and then all of that wrapped in a ReLU. And then from here we can print out our layer 1 out, and then also print out the size of the layer 1 out just to see what we have. So yeah, that's our layer 1 output. Yeah, it's pretty long actually, but yeah, here's the shape of it down here. So we still have our 10 samples in the batch, 10 images in this batch that we're dealing with. But now we have the output values for those 128 neurons. Okay. Whoops. Sorry, I'm just, yeah. Okay. So yeah, that's our first layer. And then layer 2 is gonna be pretty similar. It's gonna copy and paste again. But yeah, layer 2, which is gonna be our last layer. This is only going to have 2 layers in this neural net. So layer 2 is gonna take is gonna be taking in 128 inputs from the 128 neurons in the first layer, and then it's going to have 10 neurons in the second layer. And then each of these 10 neurons is going to correspond to one of the possible digits. So we have 10 possible classes that each image can be labeled with, from 0 up until 9. So there's 10 possibilities for what digit each one is, and we want to have our final layer output numbers like to correspond to guesses for each one of those possible digits basically. So yeah, we're going to say weights equals tensor, and then like random initialization, 128 rows corresponding to the 128 inputs, and then 10 neurons in the second layer. So that's why we have 10 columns, and each one of those corresponds to one of our classes that the image could be labeled with, basically. And then the biases for the second layer, again, same idea. We're just going to initialize them as zeros, but these will eventually be able to be updated if we want them to. And then, okay, the actual pass-through layer 2 is going to look like this. So we're going to say layer 2 out equals layer 1 out times weights 2 plus biases 2. And then at this point, we can print out this layer 2 raw output, which if you guys remember, this is what we call like the logits. So this is the raw output of the neural network before it gets turned into probabilities. So we can print that out and also print out the shape of it for a little like shape check. And yeah, that's the raw output, and the shape is 10 by 10, meaning 10 images, and then for each image we have a raw output number for each one of the 10 possible class labels. And even though in this example they kind of look like they could be probabilities, these actually haven't been through the like softmax activation yet, so they haven't actually been like officially turned into probabilities yet. So we'll do that next. But this is remember like the logits output they call it. Okay, so what we want to do next is we want to be able to calculate the loss by comparing this like raw output to the actual answers for this batch. So the eventual function that we're gonna call is gonna be our softmax cross entropy function, which remember does the softmax, which means turning this raw output into probabilities with the softmax activation function, and then the cross entropy loss, which is a way of calculating like how far off the model is from the correct answers. Yeah, basically rewarding it for having probabilities close to 1 for the correct answer, and punishing it for having like high probabilities for incorrect answers. But to do that, we need this like one hot vector of the correct answers for this batch. So to get that, we're gonna first say batch y equals y train. And you know what? Maybe I'll actually put this up at the top to just make it easier. So yeah, batch y equals y train from 1 to 10, so that we have the correct answer for each image in our batch. And then we're going to cast this. Or sorry, I forgot. No, we do not cast this as a tensor. That's the one thing. Yeah, I'm not really happy about. I want to eventually fix that, but yeah, right now the correct answers should just be a regular array, not a tensor. Okay, so at this point we could just like print out our y batch and just take a look at it. Whoops, sorry, I called it batch y, and yes, that just tells us like for each row in our like X batch, what was the correct digit for that row basically? What was the actual digit that the image was a drawing of? So that's just our correct answer array here. And also guys, don't worry if you're seeing different numbers than me. This was all just shuffled randomly, so it could be different numbers for you guys. Maybe I should have like seeded the random number generator so it could be exactly the same, but I forgot to do that and it's too late now. So yeah, don't worry if you're seeing like different numbers than me here, because yeah, it's just randomly shuffled. But yeah, these are our correct answers, but we want to get this into one hot encoding. So we want to get this into like an actual matrix where it's a 0 at every element that is the incorrect answer and a 1 at every element that's the correct answer. So to do that, I'm just going to actually just copy and paste a little bit of code here. Yeah, it's going to be copy and pasting. I just got to change a couple of small things. So yeah, I'm going to say like batch y 1 hot equals zeros, batch size, which is 10 in our case, and number of classes, which is 10 in our case. And then yeah, for batch int and batch size, batch y 1 hot. And then yeah, there's just some code to make it into a 1 hot encoded matrix basically. So yeah, then we can print this out, and then whoops, forgot something here. Forget anything else? Yeah, so this is basically like a big matrix where like every row here is, whoops, sorry, that was actually 2 rows. But yeah, every row, like this is one row, for example. Every row has one element labeled with a 1, and then 9 elements labeled with a 0. And the element that's labeled with a 1 tells us which element is our correct answer. So this is the like 6 element here. So it's, yeah, like 1, 2, 3, 4, 5, 6, 7. Oh, sorry guys, I forgot, because it starts at 0. So actually, yeah, it starts at 0. So the digits, the digits start at 0. So it's actually our 7th element that corresponds to the digit 6. So the elements here are like 0, 1, 2, 3, 4, 5, 6. So actually it's closer to like Python indexing, because it is like a 0 index matrix basically, because yeah, our first digit that we had the hand-drawn digits of was 0. So yeah, this corresponds to the digit 6, and then yeah, so the second row we have 0, 1, 2, 3, 4, because 4 is our correct answer. And then same thing for each of these rows. It tells us with the label 1 which one of these elements corresponds to our correct answer. And then the zeros tell us all the elements that correspond to the incorrect answers for that image. And then yeah, once we have that, we can compute our loss here. And then we can print out the loss. And then if you guys remember, this loss number just tells us like how wrong our neural network model currently is in terms of classifying these images. So the higher this loss is, the worse the model is doing, and we want it to be close to 0 if we can get it close to 0. Okay, now this next line is where basically all the magic happens, and everything we've been doing in this whole project so far, like, actually gets used to do what we need to do to like solve this problem. So this is going to be the one line that like is the most important line, where we can really see that everything we've done is going to allow us to like actually solve this problem. So that line is backward loss. So what this line does is it does the full backward pass to calculate the derivative of this loss with respect to all of the parameters in this model. So we can see like what would happen to the loss by making a small change to each one of the parameters. So yeah, this is like the most important line, and this is the line that we've been like building up to with everything we've done so far in this series, basically. Yeah, because this is like the magic of machine learning with neural nets, is this like back propagation and calculating the derivative of the loss function with respect to like all the parameters that went into it, basically. So yeah, we can do that, and then after that we can print out, like, for example, weights1.grad. And then yeah, this will tell us basically, I mean, it looks like at the top it's a lot of zeros, but if you go down a bit, you start to see some actual numbers, pretty small numbers, but I think that's to be expected. But yeah, this weights1.grad tells us the derivative of the loss function with respect to every number in this weights1 matrix, basically. Every single parameter in this weights1 matrix. These weights1.grad numbers tell us the derivative of the loss with respect to that parameter, basically. And the cool thing here is, before I run this again, we're gonna have to do a lot of like resetting of gradients. Basically, every time we call like backward loss, we want to first like reset the gradients to 0 so that we're not just like having them accumulate when we don't want them to. Or sorry, actually, technically we need to do this because some of these are getting calculated in this forward pass here. So technically we need to reset the gradients at the beginning of like up here, actually. So yeah, we're resetting this to 0 so that I can run this cell again and have the gradients not like build up. They should be reset to 0 with each pass we're doing. So yeah, now we can keep running this like multiple times and not have it like build up every time. Whoops, I think I actually forgot something here. Actually, I forgot. I only zeroed it for the parameters. I actually forgot to do it for the actual. I think I need to do it, yeah, for this stuff too. Make sure that, yeah, basically making sure that like everything that has a gradient is getting the gradient zeroed here. Or wait, no, I think I didn't technically need to do that because. Yeah, I think I technically didn't need to do that because this is getting, these other things are getting like recreated each time. So yeah, sorry guys, I think I don't actually, yeah, I don't, sorry guys, I'm getting myself confused here. I actually don't need to do that because these tensors are getting like recreated, no, sorry, not this one, but like these two here are getting recreated each time. So every time they're recreated, the gradients get zeroed out anyway. So yeah, I think I actually don't need to do that, so. Okay, sorry guys for getting myself confused there. But, yeah, so what this allows us to do is, now that we know the derivative of the loss with respect to all of these parameters in weights 1, we can update the parameters in a way that will basically go in the opposite direction of these derivatives so that the loss will be nudged downward, basically. So the way we're going to do that is we're going to say weights1.data. Remember, that's the actual matrix in weights 1 with the actual parameter values. Weights1.data minus equals weights1.grad. So this is basically like subtracting from weights1.data the value of the gradient. So if it's positive, we're going to be moving the parameter, we're going to be decreasing the parameter, like making it more negative. And if it's negative, we're going to be adding to the parameter, making it more positive. So moving it in the opposite direction of the derivative, basically. Because remember, if the derivative of the loss with respect to the parameter is positive, that means increasing the parameter will cause the loss to go up, and decreasing it will cause the loss to go down. So we want to move it so that the loss goes down, basically. Because that tuning is what allows our model to get better. But this will be too much of an update, so we want to actually like multiply this update by some learning rate, which we'll call LR. And I'm actually going to start making a new cell up here to define some of these what's called like hyperparameters, like the learning rate. So our learning rate is going to be just 0.1, and yeah, I'll call this up here yeah, like hyperparameters. So yeah, learning rate will be like 0.1, and then yeah, so this basically controls like how fast we're or like how much we're updating these parameter values each time. We can make this smaller to make, yeah, learning rate smaller, meaning like smaller updates, or larger for larger updates. And that tuning of the hyperparameters is a little bit beyond the scope of this video series. But yeah, sometimes you want to figure out like what the proper hyperparameters are to use to get your training to be the most effective. But yeah, I'm just going to make it like 0.1 for now. And then yeah, so this line basically is updating the weights 1 parameters according to the gradient, and just like scaling the size of the update by our learning rate here. And you know what? Maybe the syntax here is a little bit confusing. I mean, the syntax is correct, but maybe I'll actually just write weights1 data equals weights1 data, just to make it more clear for you guys, minus this weights1.grad times the learning rate. So I'll just say here like updating parameter values based on gradient. Okay, and then yeah, we basically want to do that for each one of our like parameter tensors. So we're gonna do that for weights 1, biases 1, and then weights 2, biases 2. And then, okay, maybe we'll just give this a run to just make sure it works okay. Yeah, make sure it runs without any errors or anything. But yeah, just to sum up, what this whole cell does is it takes a batch of these images. So it takes a batch of 10 images and stores them in this batch X tensor. And then we store all of the correct answers in batch Y, which is just a regular one-dimensional array. Then we're converting these correct answers to a one-hot encoded two-dimensional array. And remember, this is not a tensor, this is just a regular array, basically. I might work on changing that later, but yeah, for now it's just a regular two-dimensional array. And then we zero all of our gradients so that we can like rerun this code without the gradients like building up. Basically, for every batch, we want the gradients to start at 0 so that we can calculate them properly for that batch. And then yeah, so we pass our batch X through our first layer, which takes in 784 input features, so 1 pixel measurement for each of the images in the batch. And there's 128 neurons in the first layer. And then we also add our biases, so we get our layer 1 output. And then layer 2 takes in 128 inputs from the 128 neurons in the first layer. And then layer 2 has 10 neurons, which corresponds to the 10 possible answers, 0 to 9, of what digit each image might be, basically. And yeah, we do our raw like pass through layer 2 to get the logits, which is our raw layer 2 output. And then this softmax cross entropy function does the softmax to convert the layer 2 raw output to probabilities using the softmax activation function. And then cross entropy computes the loss for that batch, which, remember, like a higher number for the loss means that our model is doing bad, and then a lower number means that our model is doing a good job, basically. So we want the loss to be like pretty low, so that our model will be doing a good job with these predictions. And yeah, the backward loss does the full backward pass. So this is, like I said, like the culmination of everything we've been doing, basically, in this whole video series. This backward pass is like this one line here is doing like all the important things that we learned how to do in this whole series. And then yeah, from there, that calculates the gradients of all of the parameters. And then once we have the gradients of all the parameters, that tells us the derivative of the loss with respect to that parameter. And so that derivative tells us how we should update that parameter value in order to get the loss to go down, basically. So then this couple lines here is how we actually update our parameters to tune them to hopefully get the loss to go down for that batch, at least. And our hope is that decreasing of the loss will generalize over time across like to the different batches, basically. Okay, so now I think we're ready to start like putting this in a big for loop to actually do our training. So I'm gonna say, to put all this in a for loop, I'm gonna say for I in one batch size X train 1, and then end, and then indent all of this. And we need to also define what our batch size is. I'm going to define that up at the hyperparameters and make that batch size equals 100. So 100 images in each batch. And then yes, this is basically like iterating over these numbers. And so yeah, this is basically giving us an index I going from 1 to the size of our the size of our X training set in steps, where each step is the batch size, basically. And then yeah, we're gonna change some of this from 10 to batch size. Oh, whoops, sorry. This should actually be not just 1. This should be I going to I plus batch size minus 1. Same thing here. I going to I plus batch size minus 1. And then yeah, I'll just say batch size here. This is the number of classes. I'll make that another hyperparameter. Up here, num classes equals 10. And then yeah, this was batch size, okay. Okay, so this for loop that we have now will go through and divide up our training data set into like batches of 100 images, and then do the training and updating of the parameters for each one of those batches. So yeah, maybe I'll just clean up a little bit here, remove some of these comments and stuff. Yeah, we can delete these. Okay, so that'll go through the whole training set once, but we actually want to go through and yeah, like go through the whole training set a couple times. So I'm gonna say for epoch in 1 to epochs, and then this whole thing is gonna be indented, and then end that, and then I'm gonna say epochs equals 3, so that we basically are going to go through the whole training set 3 times to really do like a thorough training. And then yeah, one last thing, I want to be able to like track our progress while we're doing this. So I'm going to keep track of what actual number training run we're on too. So I'm going to say global run equals 1, global run plus equals 1. And then I'm going to put in this line here just to track the progress. Yeah, if run is divisible by 10, then we're going to print out the epoch run, the run number, and then the current loss, basically, just like track our progress in the training. Oh, whoops, sorry guys, I just caught myself in a huge error here. This this is embarrassing. This would have been like a huge bug in the code. Yeah, I realized that the way I have it written now, it's initializing the parameters like with every new batch that it's training on. It's like it's redoing this like initialization. We need to get these out of this for loop and just have them up here basically. So yeah, I'm gonna say like initializing parameters. So yeah, sorry about that. That would have been like a huge bug, and I probably would have been confused about like why my code wasn't working. So yeah, we're just gonna we're gonna grab both of these actually. So yeah, in order to get these parameters actually being trained and tuned, we can't have them being redefined randomly with every new batch we're doing. We need to get them defined in the beginning, and then we're gonna be updating them within this nested for loop. So yeah, sorry about that error. Huge error on my part. But yeah, I'm glad I caught it at least before I started actually running this code. So yeah, we want to define these parameters up top like this. Okay, we'll initialize them to start up here. And then yeah, make sure that we're good down here. Okay, I think we're ready to actually like run this now, and hopefully it'll work okay. But yeah, I think we're ready to actually like run this and do our training of the model now. Whoops, sorry guys, I did this, yeah, another embarrassing mistake. I did this, updating of the run number, I just forgot the equal sign there for the, increment. Okay. Okay, looks like it's working. So, is it done yet? Yeah, it's actually done training. So we can see it starts off, when it's starting, it has a pretty high, loss up here. Pretty high loss, but then we can see over time we're tuning our parameters, and it's the loss is going down over time. And even though these are all different batches, the tuning of the parameters is generalizing from batch to batch, basically. So over time, it's tending to get lower until it gets pretty low, and then our progress starts to like stagnate a bit. But yeah, towards the end, we have a much lower loss than what we started with. So that hopefully means that our model is tuned pretty well. But yes, that's the training. The next thing we're going to do is actually test out this now trained model on our testing data set. Okay, now for this part, I'm going to be a little bit lazy and copy and paste a bit of code, because this is starting to turn into a pretty long video, and I don't want to keep you guys here like forever. So I'm going to be a little bit lazy and kind of breeze through this last part, hopefully. But yeah, this is the code for the testing. So it's like I mentioned before, the reason we split it up into training and testing sets in the beginning was that we want to be able to test out how good of a job our model is doing now on some new images that it hasn't already seen yet. And it hasn't seen these X test images. Those are the ones we left aside to use for the testing, so that, yeah, the model hasn't been trained on these. It hasn't seen these ones yet. So this will give us an idea of how well it does on new images that it hasn't already seen in the training. And then, yeah, so this block of code is basically just going through our X test images. And then for each one, it's like just pulling out that row for that image, casting the row as a tensor, and then getting the correct answer, and then passing that tensor through the neural network like this, basically. Passing it through the neural network, and then taking as a guess whatever element in the output has the highest value. For this part, we could convert to probabilities if we wanted to and actually compute like the loss. But for now, we're not looking for the loss anymore. We're just looking for an actual prediction of what number it is. So we're just taking the maximum value of this layer 2 output, and that whatever index element that is our prediction. Although to be precise, it's the index -1, because our digits start at 0. So if it's the first index with the highest number, then that is the element that corresponds to the 0 digit, and the second index that corresponds to the 1 digit, and so on and so on. So our whatever index has the highest number, that index -1 is our model's prediction about what number that is in the image, basically. And if we get it right, then we increment our correct number. And then if not, then we don't increment the correct number, but we increment the total number no matter what. So we can go through like that, and then at the end we can print out the accuracy, which is the correct divided by the total. Yeah. Whoops. Got something wrong here. Okay, sorry guys. I thought I remembered how to do like this string printing in Julia, but I guess not. I'll just you know what? I'll do it the old-fashioned way. Yeah, just doing it the old-fashioned way here. Okay. Okay, so 91% accuracy. Pretty good, if I do say so myself. I think that's pretty good because remember, there's 10 possibilities for each image. So if it was randomly guessing, it would be getting about 10% accuracy. It'd be getting about 1 in 10 correct. But after this pretty simple training that we did, again, very cool because we did this training all from scratch with a neural network where we wrote every part of it from scratch. Didn't have to import anything for this neural network. Wrote everything totally from scratch. And yeah, after doing that training of our neural network, it's getting 91% accuracy. If we want to be generous and round up, even 92% accuracy. Yeah, so pretty awesome, if I do say so myself. Yeah, this is really cool. And yeah, if you guys have made it this far, I'm proud of you for sticking with this. I think it's very cool that we did this from scratch. We did every part of this from scratch. And then, yeah, we trained it on like a real machine learning problem, classifying these images. And then, yeah, we're seeing now it actually has pretty good accuracy. There's one more thing I'm going to show you guys. So there's one more thing. And again, I'm going to breeze through this pretty quickly, but, if you want to make like a little user-friendly function to get classifications for individual images, it'll look a little something like this, basically. So yeah, maybe I'll just call this like user-friendly function. So this is a little simple function I wrote that takes in an image path and then does this loading of the image and converting the image to a tensor, and then it passes the image through the neural network and then gets the actual like prediction of the number at the end, and then prints out the guess of what the predicted digit is. So we can test out using this too. Yeah, for this part I was thinking we actually can use these like test set images. even though they don't have the correct label, we can just look at what label they are. So, okay, let's see. This first test set image is image 1, and it's a 2. So we can see, okay, let's try passing this, passing this image into our little user-friendly function here. Oops, make this image 1. Let's say guess digit, image path, and yeah, prints out guess 2. And yeah, got it right. Can try now the second one. This is a 0. Guess 0. Okay, got it right. Try out the third one. This is a 9. Yeah, got it right. So yeah, pretty cool. Yeah, I think this is awesome. I'm very happy with how this project turned out, and I hope that you guys are happy with it too. And I hope that you had fun and learned a lot. I really like these projects of like building things from scratch, because when you build something from scratch, it lets you understand what everything is doing like at every step of the way, so that like nothing is a mystery. So I hope that that's what you guys got out of this project. I hope that this was helpful for you guys learning about both like neural networks and like Julia programming. I hope this was like a useful learning experience. Thank you guys for sticking with this all the way through these whole like 18 videos. I know this was a long series, but if you guys made it this far, I'm very proud of you. Yeah, I hope you guys found this helpful. And yeah, that's basically it. That's basically it for this project. Any questions you guys have, just let me know in the comments and I'll try to answer them. Like usual, all of the code is up on my GitHub. The link will be in the description if you guys want to download the code for yourself and try it out. Oh, and just again, this whole project was based on this real package that I made, SimpleGrad. So this is like a real package you can install and use in Julia. Although I guess at this point you guys don't even need to install the package anymore, because you guys now know like how to actually write this yourself. So yeah, there's no point you guys even using this package, because you guys can just make it for yourself if you want to, basically. But yeah, if you want to, this is the package. Here's the GitHub if you guys want to check out the GitHub repo. It's supposed to be like a educational package, basically. But yeah, this video series was basically just showing you guys like how to make this SimpleGrad package that I made. Yeah, so I hope it was helpful for you guys. Hope you learned something. Thank you for sticking with this series. And yeah, that's it. So thanks for watching, and see you guys next time.